Hi everyone, so welcome to my second stream on this project, CleverHand. So today we will try to start with a sum up of where we left yesterday and try to progress on our PCB design. So first let's try to make some nice diagram, nicer than yesterday at least, of the project structure. So draw IO. Okay, so the idea, as I was telling yesterday on the first stream, so would be to have an EMG recording device. So EMG back. Oops. Okay. This EMG acquisition device should be able to connect to different type of electrodes. I'll try today to make it to make some example of electrode type that could be. So type A, for example. Type B, for example. Let's make it a bit smaller, maybe. Tuk. Okay, this one we can make it smaller as well. Yep. And one thing that is very important and that is missing from a lot of EMG bracelet or at least EMG module is the fact that the communication layer is not very practical and it's always very specific to one application. So here I'm trying to make a communication layer that would be a bit more modular and that would let you create a lot of different combinations of the different module. So the communication module, for example. Communication. Okay, and so you have this, and then maybe we can put it inside another one. So let's imagine that would be a module and you would want to be able to communicate. Let's put it in a row with several of them. Yep, okay. And then, oops. So yeah, sorry, it's taking some time, but I think it's quite important that we have a nice drawing at first, and this way we can refer to this for next for the different stream or progress of the project. Okay, we have this. All of them should be able to communicate together. So, oops. Something like this. Not pretty. this. Okay, and this one goes there as well. Tuk. Here. Okay. Right. It looks a bit nicer. Oops. Okay, up, and then so all these modules, as I was saying, should be able to communicate between each of them or share a common bus. So there is no real direction. Don't know how to do that. Like this. Yep. Okay, and you have a master module. Microcontroller. That should also be able to connect on the same bus. And this same guy should be able to communicate with a computer. But also synchronize with another microcontroller. So we want be able to do that. So yes, so this one should be able to synchronize with this one. So let's try just like this. I will try after to add some more information on the diagram. The more we go on with this project, the more this diagram should look like something, and we can try to follow the progress from here. So this one is not really directional, so let's try to remove maybe this one. None. Okay. And this one should be able to communicate with the computer. It's bidirectional. Okay, here we go. Yeah, I think that's kind of what the structure look like. If we want to add some information, so let's put some text. So yesterday I was saying that the computer and the microcontroller should be able to communicate using USB, Ethernet, or Wi-Fi, for example. And what I choose to make the different buses, the bus between the different module to communicate together is SPI bus plus, and that is let's say the small characteristic of this project is this addressing part that I will try to describe today. Addressing system. because as I was saying, so since I put some requirement on this project, I wanted to be able to connect at least 16 modules together. So it was important that it was, let's say, modular, and you can put as many as you want, and you should be able to address 16 of them. Yesterday I was describing the SPI protocol. The SPI protocol is working with 3 shared wires, so the clock, the data input, the data output, and what is very important is that each module can be selected independently. So each of them knows when they are talked to or when they should reply. So let's say the naive way would be to add a wire for each of them to be able to activate them when we need to talk to them. The issue is that if you have 16 of them, then it means that you need 16 wires to talk to the 16 module, which make it not very practical, and you would end up with a bus here with a lot of wire. So if we sum up the wires, let's say, that are needed in this bus, we would need a power supply, so the VCC and GND. You would need, as I was saying, so the SPI MISO. So MISO is master input slave output. SPI MODSI for master output slave input, and SPI clock for the clock signal. And so that is the very, let's say, fundamental and basic one. If you were to create a naive version of the SPI protocol, you would need chip select 1 to chip select 16 if you want a 16 module, and that is creating, so here you have 5 plus 16, so you end up with 21 wire and 21 wire. So if you want an example, this one is an FPC flat ribbon. So this one contain, if I'm not wrong, 18 root, 18 track on it. So this is already, it's close to, it's already not enough for this communication. And here we are using only the fundamental one. So maybe we need some other function in this bus. So we would need very large, for example, FPC cable or a lot of wire. So instead of doing this, also, yeah, another issue with this addressing system would be that on your wires, you have, for example, on a ribbon, the place of each of these track is fixed. So that means that if this one wants to use the chip select 1, because it is the first one, and it means that this communication module should be connected to, should know that it should look at the CS1. This one should know that it should look at the CS2. This one should look at the CS3. So to do that manually, you would need to solder some pins or to put some resistor to select kind of the address of each pin. But it means that each module would have a determined address, a fixed address that could not be changed at each usage and all. And for example, if you wanted to create something modular, then that would mean that you have a module that is module address 1 that cannot be put at the place of a module address 2, which is very constraining. So to fix that, what I tried to do is to create an addressing system. So using, at first, we will see if we make it bigger, but using 4 bytes, 4 bits to start. So this system, I think I have a nice description here. What I started to do was the following. So you have your master controller that wants to communicate with a given module. The master should not know exactly where the EMG device is in the bus. So it's important that this addressing system change, let's say, depending on the position of the module in the bus, so the physical position. So if I plug EMG directly to the master, this address should automatically be address number 1. If I plug a module at address 2, at the second place after the module 1, then the address should be 2. And this should be done, should be able to be, the user should not have to decide. So this is just the position that create the address, let's say. So here, the system I decided to use is the master send an address, for example, 13. It send it to the first one. The first one read 13. So 13, all the bits are not 1. It means that the master was not talking to this one. Then he takes the address sent by the master and propagate it to the next one, but incrementing it. So now this module is sending 14 to the next one. The next one is reading and seeing that all the bits are not 1. So the master is probably not talking to this one. So it takes the address, increment it, and send it to the next one. So now the address sent by this one is 15. This one reads the address. Oh, he sees that all the bits are 1. So it means that the master is speaking to this one. So the master can send an address like this and address a specific module on the bus without having to rely on a fixed addressing system. So every time you place a module on the bus, its physical position will imply its SPI address. To do that, what you, let's say, just need is some logic gate to increment the value of each of them, of each bit. And you can create like this something that is very fast at propagating an address. So for example, in the case of this one, I was using, so here you can see those two microcontroller, or those two chips are actually logic gate, and they are able to they are able to realize this incrementation system. So it's adder 1 structure. So you just, this input address result in the same plus 1 address, and you read and you use this how's it called already, reminder, to control your controller, the EMG acquisition system. So this way, if you try to add 1 to this and it gives you a 1 here, then it means that it is supposed to talk to this one. But you can see that even if you can do it with simple logic gates, the simple logic gates are quite big, and it's taking more space than the analog, than the EMG chip. So it's a bit it's a shame, and I was trying to find maybe a better solution. So the space is an issue, but also the fact that you need to solder them, and it is a lot of pins. So for example, if someone wanted to do it by hand, then it is a bit tricky. It's also adding some price, because if you need to buy several chips, then I think each of them is around 50p, but still it is some price adding up. And actually, so you need 3 chips. This one for the NAND gate, this one for the NOR gate, and this one for the simple AND or something like this. So I was trying to think of another solution to reduce the space. So in this solution, I came up with the idea of, instead of doing it in a hardware way, why not using directly a microcontroller? Because I discovered this ARM microcontroller, which is super cheap. It's 50p, just this one, and it is able to do, you can program it, and you can use, I think, up to 16 GPIO all around, and so this way, this mechanism, you could do it directly just by software. So this chip should be able to add 1 to the input pin, and to propagate with +1 to the output pin. So I tried that. However, one thing I didn't consider is, if you look at those pins, so those let's try to see. KiCad 81. Maybe I can open directly my computer. Hop. No, probably not this one. Is there? Let's try to see. Nope. So this one is the one I was showing you. So this ARM controller is HC32L110. I will talk a bit more about this one after. So not this board. Project. Logic address, probably. Yep. So you see here is the incrementer system with AND gate, XOR gate, and an AND to be able to activate the chip select. So if you see, so those chip, if you look at them online, one thing I didn't realize when I chose them, and I was quite lucky, is that the propagation time, so the time it takes when one input change to create a change on the output, is only around 3 nanoseconds. So it's very, very fast. In comparison, the HC32L, this guy, very, very small, you can see. However, it is it written? Yep, it is a 32 megahertz chip. So if you take calculator, 1 divided by 32.3 to get 32 megahertz, you can see that it is already 31 nanosecond. So one how would I say, one basic assembly command action would already take at least 31 nanosecond to be done. So adding bits, so reading bits, adding one to them, and then writing those bits outside. I did some tests to try to do it the most optimal way by if we look at it, oops, let's see, open folder. Inside where was it? CleverHand. Did I write it? Probably in this one and this one. Oops, let's open just. Okay, if you go in user main, so I tried to make it super optimal to write assembly code to do this bits adding, so to be able to have a binary adding system. And you can see that you need few lines. You need 50, 53 minus 30, so you need around 20 command, 20 to 30 instruction, assembly instruction. So it means that your microcontroller will take this time, let's say 30. Oops. So it will take at least it will take 1 microsecond to change, so to be able to propagate, which is a lot slower, but it is 100 times slower than what I had with those logic gate. And it is very constraining because the objective is to be able to send, so I was saying 16 module. So on the SPI bus, I should be able to send the data from 16 module. Each module has at least 3 EMG channel. Those 3 channels have at least 3 byte resolution, so 3 bytes is 3 times 8. Okay, and you want to be able to communicate at we said 2000 hertz. So you reach 2 megahertz. So it means that you need that you each let's say each bit that is sent in the bus should not take more than half a microsecond. So with this system you're already very limited, and you might be able to reach 1000 hertz sampling rate, but yeah. So you could do something, but it's not optimal. So I started thinking about again another solution. I think on the video version or on the cut version, I will try to put more diagram to make it easier to understand. So now the final, hopefully, solution I came up with is to use a combination between this microcontroller. This microcontroller is very nice to have some computational power on each module. However, it is not fast enough. So one thing you can do is combine a comparator. I think for bit. So you could use this type of thing, and so the B here would be connected to the microcontroller, and the A would be connected on your address bus. this way on the bus, if you see the bit that is the same as your microcontroller set at the beginning, at the initialization, then if it's the same, it will it will activate something. So if you use it on 4 byte, I think it was written here. Do I have something here? Nope. Let's go back to here. Open here. Oh. Maybe I don't. Maybe I don't have this this version here. Let me try to find it again. Hop. Sorry for that. Okay, so I think I should be able to find it. Oh yes, I saved it on GLC PCB. My file, part manager, part lib, part cards, and here, yep, this one. So see the price, very, let's say, affordable. And can I copy paste it? And when you look at it, so first, what is nice, it's 8 bits, so that means that we could maybe extend it to more than 16 address. And this is exactly what it is doing. So this every Q pins would be connected to the microcontroller and would be predetermined at the beginning at initialization. It would initialize its address, and all of the other P pins would be connected to the bus, to the addressing bus, and it would be able to compare every time. And if all the P bits are all equal to the Q bits, then you are able to select your chip. And this one, you have your propagation time that is again a lot smaller, bigger than the logic gate, still a lot slower, a lot faster than the microcontroller. So we will use probably this one. So if we put it here, are we able to increase? How should I do? Took maybe something like this to back. So those are the one we need, and the chip we're going to use will be, for example, this one. So it's called 8-bit identity. So identity comp. We use this. We will use a microcontroller to do all the to add functionality and to do the initializing addressing part. Microcontroller. Which will be we set the HC still here, not here anymore. So we said here. Oops. Here you go. This, you have this. Okay, so if we redescribe how it's working, you have those and text. Up. So you have those addressing bits that will go into this identity comparator, and then you will have this microcontroller that will set, if I can write on the code, set address at the beginning, and you should have, so that means also that on your communication bus you should have other pins to communicate with the microcontroller. So additional IO pin. It could be I2 square, I square, but I square C bus, I2C bus. Never said it. And those would be communicating. Oops. Here. Something like this. Good. One thing I think is quite nice on your device to be able to first to debug, but also to be able to kind of add some feedback for the users. So it can be for the scientists, it can be for the bracelet band user. It is very convenient if you have an easy feedback. So the easiest feedback would be, for example, an RGB LED. Yep, that could be controlled directly by this guy. By the way, when I did the test, I realized that to control, so for this one I already decided I will use NeoPixel 1, because you can set the LED light very nicely, but the communication protocol to communicate with them is very fast, nanosecond again, so it's a bit tricky to set this with the microcontroller, but it's possible. So I think we will go with this one, and I think that's it. Let's try to do similar one. Oh, and so the output, other direction. You end up having the communication bus, see. And oops, what did I do? What? That is not very optimal. Why? Yeah, I don't know why it's like this. Okay, you have these one are shared, so it should be exactly the same. And this one should be shared as well. Hop. So it's kind of the working schematic of this communication module. Then we would need to redo the same for the forgot one thing, which is quite important. Let me think how to make it look nice, because we need obviously the what the communication bus is required for is to select the module, the EMG module. So obviously you would need some output to control it. So up, and let's say chip select. Yes, we need the chip select, we need power, and let's see if we, or maybe shared ref. So for the, we talked about this yesterday for the EMG acquisition system. It is very important that we share a reference, a voltage reference. So we should share it with it. Maybe let's call it user ref or something like this. Or global. Okay, and this is done with this. Oops. Okay, to make it look better, I have to make it like this. This one should be moved. Something like this, I guess. Okay. Like this. So the additional pins. something like this. Okay, and then I was saying that we need to have similar diagram for the EMG DAC module. So what we said yesterday was we need so clearly this is the same input. We need the DAC, EMG ADC, analog to digital converter, which is ADS 1293. This little guy should be connected here, for example, and it will be 6 input channel. Wait. Oops. Something like this. Be able to communicate with the communication bus with the same thing actually. SPI. This we said it would be the global ref. Try to make it cleaner later. Okay, this. We said that this guy needed a crystal. Yep. 4 megahertz, 4.0.96 megahertz. One of the channel oops. global share for the global ref. So like this. Oops. This one will be the electrode type. Can I put pictures? I don't think so. Let's put some example. So it can be basic jack connectors for sticky wet electrodes. Could be pins connector for breadboard. Could be let's call it PCB gold plated surface electrodes. So yeah, so here are different type that should be possible to connect to this module. Hop. Here we go. The communication. Okay, so we can see that we need at least 5 here. Let's go to 5 now that we have a 8-bit comparator. So let's go to 5. This guy has 16 GPIO. So it means that 5 are used for this. So 11 left, 11 and 10 left if we use one for the NeoPixel. So we still have 10 unused one. So we will probably not use all of them, but we need at least some of them to program the microcontroller and to communicate, for example, for the initial part, so for the communication to be able to set the address. So let's say that we will use, for example, 5. So now we are at 5, 15, 16. So the FPC ribbon I'm using are 18. That means that I still have 3 unused. So for now, let's put them. Good thing when you design is that you never know. So let's use 3 auxiliary that should be able to be accessed later, and this one we can use them to debug or to add some more features later. Okay, so we have a communication bus of 18. Okay, so I think it is starting to describe the process a bit better. Yes. Okay, so for today I think we will just try to make this one look a bit better, or to make a board for this one. And then no, we did for this one last time, so now we will try to make a board for this one. Hop. If we create a new one, let's call it similarly CleverHand com module. Okay, let's put this one in. Oop. So we said that the name of this chip, of this identity comparator chip, was SN54. Oopsie. I don't have it. This is annoying, so let's download DGK KiCad library. Our library, GitHub. Oop. Here you go. Let's download it. Let's extract it here. Source. Okay. Don't remember the process to do that. Organization, installation. Here. Maybe it would be helpful. Okay, let's try. So you will see how the library management. Oh, by the way, maybe I'm saying that, but maybe we can find it from here. Nope. Do we have something maybe a bit? What if we check here? DG thing. Okay. Nope. Okay. Oh, I have it. I should be able to find it. Symbol. Interesting. Oh yeah, because it's not a 54. Okay, yeah. Okay, I was not searching for the right one. It's SN74. Okay. Toop. Okay. What's this? Okay. Here you go. I also wanted the HC. 32. Weird. Never mind, let's find it. Good. Nope. Let's start again. Okay. Okay. I don't know why I was not able to find it. If we go here, will it work? Yep, it is working. Okay, If we go back on our schematic here, so we said that we wanted this and we want a NeoPixel. That's it. Okay, we want to use the same connectors. We will use 2 of them. Direction will matter, so that's why I'm putting it in the opposite direction. Here you go, this one you want it closer to this one, and yes, so you will have some of those GPIO pin connected to the P, some of the and all the addressing bits will be connected to the R, and then you will have the output here that will be connected to another output, the output of the board. The board, if we go to connectors, so we said that it should be able to provide SPI, CSS, so 3, 1, 2, and 1. So it will be 3, 5, 6, 7, at least 7. So let's do 8. Something like this. We might add also some test point to make it easier to debug later. Okay, if we update, we have this. Okay, if we draw our board, very simple board. I always prefer to start to simple, like round origin here, for example, and let's make it 20 by 24 to start. Okay, so we have this. Again, here it's not very important to have the names, so I prefer to remove them. Then we have our identity comparator. We have this. I think it will be, since this board will be horizontal, it doesn't matter too much. It is possible to put them one facing another. We will have this, and I forgot to assign the footprint for the connectors. Here you go to basic one like this. Okay, and we'll put them for all. Up, and we can update, and you will see. Ta-da! Again, you can remove text. Let's put them all. Oh, yeah. Well, we'll see later. Maybe we'll have to rearrange the order, but let's see later. Let's use a standard spacing of 2.54. Here you go. Up. The last one. Something like this. We might not use such big straw hole. Do we need it? Do we need to be this big? Because compared to the rest of the board, it seems to be overkill. So maybe let's use another one. Let's use 1.27 vertical. Up. If we update, ta-dam, and we put okay. So it is a bit smaller and maybe a bit more adequate, let's say. So we can have this guy on one side, no problem, something like this. This can, let's put this guy back. Let's put this here, and we are constrained by the size. One like this, up. Like this. Okay, then we'll have this. We have to move in the middle. Still a lot of space, unused space, that we might want to use for something else. We'll have to think about this. And okay, if you look at what it looks like, you will have your board like this. Might be good to not have on both sides the component to make it easier to solder. So maybe this one we put it back front. This way, and this way it should be easier if we want to solder this against another board. It'd be a bit easier, and maybe, oh yes, something we might have to think about is to add a whole connecting system. Not so much space here. Tuk. Where could we put a... Oh yes, maybe. So one thing I thought is quite useful is that when you don't have the space to make through hole, so for example, if you wanted to make a connection, to make a hole like this, for example, to make it possible to put a screw later and make it easier to attach it. If you don't have the space for that, one thing that you can do is drawing ball on backside, draw this, put it filled, so with no width, up, and then you make a on the backward mask, you make a similar one, a bit smaller. Up. And now, oops, was it not the right one? I'll paste. No. Oh, they put it on the same one. That's why. So we want it on the mask. Yep. So now you will have this pad accessible, and on each on which you can solder an insert, a metallic insert, something like this. Insert screw. Yep. So with some solder paste, you will be able to solder this type of insert and have an easy way to attach it. That's one way. So maybe we would just do something like this. Okay. So this board is 15 by 15. Check on our one. And that is quite small. Okay. If we open it next to the other one, so this one is the one we designed yesterday. So this one is beyond the dock. Okay, and similar here. Oops. Okay, so on this one we said that maybe we don't want to use this type of oops. Maybe we want to use maybe all of them. We use this. Up, we can update it. Okay, this way we can save some space. If we go back here, make it 15 then. Up. Okay, so this way we have something similar to this. thinking if there is a better way or not. Yeah, no, I think that should be good. I think we can do take these, move them back on in the center. Same here. Like this. Okay. This guy, we can put it back in the middle. Okay, start looking like something. This we can make it a bit smaller. This also. That is another thing I like to do here, is to make it easier to select stuff in the middle. You can draw. Actually, you can even put it on another less thing like this, and this way, if you select them all, you can select. Oops. Select in the middle. To that, to go back here, to move it here, and this one should be able, if I take the middle, to move it in the middle. And now I can go back here, 0.5. Up. Like this. Good. Up. Similarly, this one. Okay, I think that should be all for today. It was not very dynamic stream because of this initial phase of making sure that everything is well set up and that you have all your ID quite clear. So next time we can start from there and directly go to the PCB design. Okay, so see you guys.